Suppose that n independent and identically distributed random variables X1, 2 to n are observed. The random variable R, defined by X parentheses n minus X parentheses 1, is called the range of the observed random variables. In this video, we will study the cumulative distribution of the range of some observed random variables. In order to clarify the concept, let's look at the following numerical example. Suppose 5 random variables are observed in this assignment of values. The smallest is given by 0.1, which is the number of X sub 3, and the largest is given by 0.75, which is X sub 1. Therefore, the range as the difference between the largest and the smallest is just 0.75 minus 0.1, which is 0.65. Now we want to derive a general formula for the cumulative distribution of the range R. So we suppose that the random variable xi have distribution function F and density function lowercase f. Since the range R is defined as the difference between the last order statistic and the first order statistic, what we're going to do first is to find the joint density function for those two order statistics. We introduce the joint density function for the ith and the jth order statistic first. This formula could be obtained by integrating the joint density function of the whole collection of order statistics. The approach is the same as the one that we used to find the density function of just the ith order statistic in one of the previous videos. When we realize this general formula to the first and the last order statistic, the expression becomes rather simple. It's just n factorial over n minus 2 factorial times F of x sub n minus F of x sub 1 to the n minus 1 power times f of x sub 1 times f of x sub n. With the joint density function, we can start to find the distribution function of the range, which is simply the integral over the given region xn minus x1 less than or equals to a of the joint density function. Note that the joint density function expression is only valid when x sub n is greater than x sub 1. Hence, in terms of x sub n, the integration limit is going to be from x sub 1 to x sub 1 plus a, because we like xn minus x1 to be no more than a. On the other hand, your x sub 1 is allowed to range all the way from negative infinity to positive infinity. To evaluate this integral, we would love to make use of the substitution that y is equals to capital F of x sub n minus capital F of x sub 1. Since the derivative of capital F of x sub n is simply the lowercase f of x sub n, the density function of the random variable, the integral could be rewritten as n factorial over n minus 2 factorial, the integral from negative infinity, times the integral from 0 to capital F of x sub 1 plus a minus capital F of x sub 1 of y to the n minus 2 power times f of x sub 1 dy the x sub 1. After simplification, this expression could be written as n times the integral from negative infinity to positive infinity of capital F of x sub 1 plus a minus capital F of x sub 1 to the n minus 1 power times f of x sub 1 dx sub 1. And this is our general expression for the distribution of the range. In some cases, the distribution function of the range can be evaluated more explicitly. For instance, let's look at the following problem. Suppose that all capital X sub i's are uniformly distributed on the interval 0 to 1. Find the distribution function and the density function of the range. Recall that the density function and the distribution function for the random variable capital X sub I is given by these two expressions. When we plug them into the general formula for the distribution function of the range, the integrand will only be non-zero in between 0 and 1 because the lowercase f is only non-zero in this region. Moreover, we can split the region from 0 to 1 into two parts. In the first part, when x is in between 0 to 1 minus a, capital F of x1 plus a is just equal to x1 plus a, and capital F of x1 is just equals to x1. So over this part, the expression of the integrand is simply given by a to the n minus 1 power. Meanwhile, from 1 minus a to 1, the first term, capital F of x1 plus a, is going to be constantly given by 1, and the second term will still be x sub 1. So the integrand of this part is given by 1 minus x sub 1 to the n minus 1 power. The first integral is straightforward, and we will end up with n times 1 minus a times a to the n minus 1 power. And the second integral is not difficult. If we make use of the substitution that u equals 1 minus x sub 1, then the integral can be transformed into the integral from 0 to a of u to the n minus 1 power. Hence, we obtain the distribution function for the range, in this case given by n times 1 minus a times a to the n minus 1 plus a to the n for a in between 0 and 1. The density function of the range is simply the derivative of the distribution function of the range with respect to a. Through computation, we end up with n times n minus 1 times a to the n minus 1 power times 1 minus a, when a is in between 0 and 1, and 0 anywhere else. And this concludes our first example. In the second example, we want to derive the distribution of the range of a sample of size 2 from a distribution having density function f of x equals 2x when x is in between 0 and 1. Let's find the distribution function for the random variable first. When x is in between 0 and 1, the integral of the density function 2t is just given by x squared. Thus, the distribution function capital F of x is given by 0 when x is less than or equals to 0, and is given by x squared when x is in between 0 and 1. Beyond that, the value of the distribution function is going to be simply given by 1. To find the distribution function for the range, we need to solve the integral according to the formula. But since f of x sub 1 is only non-zero when x sub 1 is in between 0 and 1, the integral region could be limited to the interval from 0 to 1, and f of x sub 1 could be replaced by 2 times x sub 1. Also, know that n is equals to 2, so those two constants could be replaced by 2 and 1 respectively. We will further split the integral into two parts. From 0 to 1 minus a, the integrand is going to be given by x sub 1 plus a squared minus x sub 1 squared times 2 times x sub 1. And from 1 minus a to 1, the integrand is given by 1 minus x sub 1 squared times 2x sub 1. This integral is straightforward but a little tedious. With patience, one could show that it is equals to this number down here. To sum up, we conclude that the distribution function for the range is given by this piecewise defined function, whose graph is given by the figure down there. Thank you for watching. I'll see you next time.